Hello, and thank you for coming back. In this and plus the next two sessions, we'll go through the common methods of underground excavation. In this session, we'll focus on mechanized excavation methods for underground rock excavations. There are a number of ways to classify underground excavation methods. Here is a summary of underground rock excavation methods based on excavation equipment used. One main method is drill and blast, using explosives to break and excavate rocks. The other main method is mechanized excavation, cutting and excavating rocks by heavy machines, including TBMs and mobile excavators. Other excavation methods using high water pressure jet, chemicals, electromagnetic heating are rather minor methods with very limited applications in large underground excavations. Key characteristics of each excavation method are summarized in the next column. We will cover in more details for drill and blast method and for mechanized methods. Underground excavations can also be differentiated by excavation processes. They can be full face excavation, multiple phase excavation, preconditioned full face excavation, and sequential excavation. Each of those methods has its unique excavation processes and is suited for specific rock masses. As summarized in the table, each excavation process has its own characteristics. For example, multiple phase excavation in hard rocks and the sequential excavation in weak rocks may both involve with multiple excavation sections. But sequential excavation is done with installing support quickly after the excavation of each section to form a closed ring, followed by monitoring and eventually open up the full face by removing the internal supports. We will have a session on sequential excavation, often referred as the new Austrian tunneling methods, the NATAM. With different excavation methods available, how do we select the suitable methods and the machines for underground excavation? In other words, what are the factors governing the selection of excavation methods? There are a number of key factors. The first one is the geometry of the excavation. They include the size, the shape, the length, alignment, and so on. For example, currently the largest rock TBM is 40 meters, and that puts the limit on size. TBM are also suited for circular cross sections, relatively long tunnels, and a large turning curvature. The second key factor is the ground condition, the geology, the groundwater, rock strength, and rock mass quality. Blasting is flexible with changing geology and preferred for very hard and strong rock, but is not able to perform under high groundwater condition. And yet, slurry shale TBM can take ground water pressure up to 20 bars. Location is another factor to consider. Is it accessible and suitable site available for TBM, particularly slurry TBM, which need a very large area of slurry separation plant. Other factors such as cost, duration, and safety. For example, TBM is capital intensive, but has rapid excavation rate. Tunneling in built-up areas are now almost all using TBMs, mainly for its low risk in settlement and in construction. Common rock excavation machines are summarized in this table here. The first group is rock breakers, rippers, picker, bucket, for relatively small size and scale excavations. Load header and the mobile miners are relatively large and designated rock cutting machines for high rate rock excavation. Tunnel boring machines, or TBM, is a complete tunnel construction system with a full face rock excavation, muck removal, and the support installation done within one machine. We'll elaborate a bit more on the last two groups of the rock excavation machines. Let us start with load header and the mobile excavators. You can see them on the right. The one on top is a heavy-duty load header, and the one below is a mobile excavator designated for hard rocks. Load header are primarily for low to moderate strength rocks. Most load headers are suitable for rocks of less than 100 megapascal strength. The heavy-duty ones could go up to 120 megapascal. Excavation performance is governed by the cut header power and influenced by rock material strength and the rock mass fraction degree. Underground excavation cycle has three basic activities: excavating, muck removing, and supporting. This is how the load head working to perform those three activities. Excavation is done by the cut header mounted with cut bits to break the rocks. This is why it cannot handle very hard rocks, as the bits can be damaged if the rock is too hard. Excavation performance or effectiveness of load header can be assessed by instantaneous cutting rate, which is governed by the equations in the box on lower right. You can see it is a function of power, rock strength, and the rock fraction degree, RQD. Muck removing and the transportation is done with loading apron and the muck conveyor behind. Load header does not do rock support. Support will be done separately by bolting machines and shotcreting. The machine can move around using the quarry chisels. The boom can reach height from 5 to 6 meters, as well as size, covering a large excavation area. The load header is flexible in terms of excavation of different opening size, shape, and length. It has relatively low capital investment as compared to TBM. The machines are ready-made and generally ready to go. Therefore, there is no need for installation time. The time between placing the order to get the machine delivered at the site is relatively short. However, there are a few shortfalls. There is no protection or support given to the rock while excavating. Therefore, load headers are used only in stable ground. As we mentioned earlier, it is suitable for excavate low to medium strength rocks with strength up to 120 megapascal. Excavation height is limited by the machine. Tunnel boring machine, or TBM, for excavating the ground with rock can be divided into two major groups: group TBM and shield TBM. Group TBM is really for excavating the rocks only, generally for competent rocks. Common shield TBM can be open face, EPB, slurry, or double shield. They are primarily developed for tunneling in soils. Therefore, when tunneling in mixed ground of rock with soils, shield TBMs are used to protect the ground from collapse. TBM cut head is mounted with roller cutters for rock excavation. They can excavate both rocks and soils, and at the same time give protection to the unstable mixed ground. Let us take a close look at the grip TBM. The main components of a typical grip TBM are shown below. At the front, it is the cut header. It cuts the full face tunnel in rocks. The cut head is mounted with many roller cutters that are responsible to break and cut the rock. The grip is shown in red. They are in pairs to press against the tunnel sides to hold the machine and to push the machine forward. Grip TBMs are suitable for competent rock masses and for strong and hard rocks with strengths up to 300 megapascal. The machine does not have protective shield. Mucks are transported by conveyors. Rock bolt machines wire mesh erector, and the shotcrete machines are also part of TBM. The photo on the left is a group TBM used for part of the 57-kilometer long Gotthard base tunnel in Switzerland. A shield TBM, on the other hand, has a shield behind the cuthead. The shield is really a metal ring to temporarily hold the ground, while people can walk inside the shield to erect the segmental lining. Shield TBM are for excavation in poor, weak, and unstable grounds. You can see the shield behind the cuthead in the photo on the right and in the drawing below. In the drawing, the shield tells at about 10-meter position, where you can see two segmental rings have been installed inside. With the shield and the lining, the excavated opening is constantly protected. Again, let us see how a TBM works in terms of excavation, marking, and supporting. Excavation is done by the roller cutters mounted on the rotating cuthead. They are pressed against rock face and breaking the rocks. Marking is removed by conveyors, except for slurry shield, which is transported through pipes together with slurry. For grip TBM, rock reinforcements by bolts, steel sets, wire mesh, and shotcrete can be installed behind the excavation. For shield TBM, temporary support is by the shield, and permanent support is by the concrete segmental ring installed inside the shield. When the TBM moves forward, the concrete segmental lining then support directly to the ground. TBM excavation, marking, and supporting is a continuous construction process. Although segmental installation is usually done while excavation is at rest. Let us focus on excavation, on how rock is cut by TBM. This involves rock fragmentation by TBM roller cutters. Roller cutters are mounted at the cuthead, spaced at typically 80 to 100 millimeter along the radius, as shown on the left photo. When the cuthead is pushed forward and rotating, the cutter penetrates and indents into the rock, causing rock to fracture. The fractures propagates and join with the fractures by the adjacent cutter and forming rock chips or flakes. This is illustrated by the figure in the middle. The indentation marks by the roller cutters are clearly visible on the right photo, shown by those concentric circles. The mechanics of rock fracturing by roller cutter is governed by rock material strength and the cut load. How effective the TBM can excavate rock is perhaps best quantified by the rate of penetration. From rate of penetration, we can estimate TBM advance rate. There are a number of prediction models to compute the rate of penetration. Some of the common models are summarized in the table. Rock parameters used in those models are indicated in the middle column. You may have noted that although different models use various parameters, however, the two main and common parameters are the uniaxial compressive strength and the rock fracturing degree. One represents the rock material strength, the other is a measure of rock mass quality. I will not elaborate those models, and you should be able to find them easily from literatures. I will just show you one example of the TBM rock excavation prediction model. It is the last one in the previous table, the project planning model. The prediction model is to provide general estimation of TBM rate of penetration at project planning stage. The model is given on the left and uses three parameters: TBM cut-head rotation velocity in terms of revolution per minute, the average load on the cutters, Fn, and FPI, the field penetration index, which is a function of rock strength and RQD, shown by the figure on the right. With shield TBM, the shield gives good protection to the ground along the tunnel circumferences during excavation. However, with very loose and soft ground, the excavation face is also unstable and need to be supported during excavation. The two common shield TBMs with face support are EPB, earth pressure balance machines, and slurry machines. One uses the excavated earth in the cut-head chamber to provide pressure to the face, and the other uses pressurized slurry in the chamber to apply a hydraulic pressure to the face. As shown by the up figure, in EPB mode, the earth pressure in the chamber is controlled by the muck removal rate through the screw conveyor. Earth pressure can build up if the muck in the chamber is removed less than the muck being excavated and then coming into the chamber. In slurry mode, as in the lower figure, slurry pressure in the chamber is regulated by the slurry coming in and then leaving the chamber through the pipes. At the same time, muck is removed together with the slurry leaving the chamber. Chamber slurry pressure can be further regulated by the air bubbles marked as 2. Underground excavation, particularly tunneling using TBM, has a number of advantages. The main and perhaps the overriding advantage is the rapid excavation rate in rocks. While in drilling and blasting excavation, the maximum advance rate is about 50 meters per day. And for TBM, the reported best advance rate is more than 80 meters per day. With powerful TBM, the machine is capable to excavate hard rocks of up to 300 megapascal strength. Full-phase excavation of tunnel diameter up to 40 meters is also achievable. Using TBM also faces risk and challenges. The key challenges is a diverse geology and the grounds, particularly mixed and challenging grounds. TBM is often selected or designed for a specific ground condition and is not ready to cope with changing of grounds. Other risks for group TBMs, EPB, and slightly mixed shield TBMs are also summarized in the table here. As we just mentioned, the most critical challenges of using TBM in rocks is the diverse and difficult grounds. TBMs in difficult grounds have been addressed by both the tunnel industry and the tunneling machine manufacturers. Common and typical difficult grounds for TBM rock tunneling includes 1. Mixed ground, such as rock-soil mixture, rock-soil interface, and rock boulders surrounded by soils. 2. Highly fractured and blocky rock masses. 3. Groundwater with a high groundwater pressure and a high water inflow. 4. Tunnel subject to very high stress at great depths and the ground is squeezing. 5. Rocks of extremely high strength and hardness and is very abrasive in nature, which causes heavy tool wearing and damage. Those difficult conditions often lead to low advance rates and high machine damages. TBMs can and have been used for mining, for both hard rock mines and coal mines. Many of the challenges faced by TBM tunneling in difficult grounds and complex geology are also faced by TBMs in mining, in terms of extreme hard and abrasive rocks, mixed ground, high stress, and squeezing. There are additional challenges in mining applications. For example, high inclinations of mine access tunnels. The TBM on the upright was a EPB mixed shield used to excavate 2 declined access tunnels at a grade of 1:6 and 1:8 for a coal mine in Australia. The excavation passed through various ground conditions, including mixed rock and soil conditions. The TBM below was designed for excavating high inclination mine access tunnels. Mechanized excavation has also been applied to shaft construction. Shaft excavation machines, including raise boring, shaft sinking, and shaft boring machines. Raising boring is illustrated on the left. With a pilot hole, the reaming machine is put and excavated the rock to create a shaft. Shaft sinking machine and the grip shaft boring machines are illustrated in the central and on the right. They use the same excavation approaches as tunneling. TBM technologies have been developing rapidly in the last 50 years and are continuing. The new foreseeable TBM technologies are 1. Hybrid TBM, for example, dual modes of mixed shield, double shield, EPB slurry convertible shield. So far, many of such technologies have been achieved. 2. Modular TBM, that is TBM parts in modular systems with fast assembly and replacing on site. The technologies have been developed and are towards achieving. Universal TBM, we always dreamed to have a single TBM dealing with varying ground conditions. We are making progress towards that. Smart TBM, a TBM with capability of self-learning and automated operation to cope with varying ground conditions. We are perhaps quite closer to that with rapid advancement in machine learning and artificial intelligence. Okay, I'm ending this session on mechanized underground excavation. Next session, we will cover drill and blast underground excavation. Bye.